Hello everyone, I want to speak about the implementation of practical digital receiver. For this reason, I'll speak about the Gardner timing recovery match filter, cubic interpolation, phase lock loop, and loop filter. As you know, symbol synchronization and phase lock loop for fine carrier recovery are important parts of receiver. Here you can see our goal is the modulation of signals like this as shown here. I focus on the modulation of offset QPSK and QPSK modulation, but for extend your receiver for the modulation of higher order modulation like QAM family, it is simply possible by just a bit change in the phase detector section and replace it with a phase detector which is proper for desired modulation order. Here we use a practical signal for evaluate the performance of algorithm. If your demodulator implemented perfectly, its output constellation should be something like this. I'll explain in detail in next slide. This receiver structure is very useful for hardware and software implementation. Despite of its low complexity, it has good performance. The general block diagram of a practical digital receiver can be something like this. Here, RF signal can be recorded, or it can be a recorded file or an output of A to D in a hardware. Assume the A to D sampling rate is Fs. The first step is drive DDS or NCO by carrier frequency of the signal, to transfer it to baseband. As you know, after DDS, you have other harmony also, so you need a low just to keep the only baseband harmony. So you have to use the low pass filter for this reason. You can after low pass filter, you can downsample the and decrease the sample frequency if your number of sample per symbol is too high based on your signal symbol rate or signal bandwidth. So use downsample for decrease frequency sampling or FS by factor of D factor. And after that, the main block, I name it Timing&PLL, just need around 4 sample per symbol. No need exact 4, just around 4 sample. Just a range of greater than 2 and a bit above 4 is sufficient after downsample. And also here, this is the main function I will explain about it. Timing, I name it Timing&PLL. The interpolator is a pioneer block here. It uses the input samples for interpolation. Somehow the timing error is corrected on it. In fact, timing controller command to the interpolator when is the appropriate time for interpolation and give a timing error value which is needed to be corrected. So timing controller decide when is the proper time and how much timing error value should be compensated in that time and command it to the interpolator. So after interpolated sample per symbol change to be 2 sample per symbol, because Gardner timing recovery timing detector only need 2 sample per symbol. So another task of timing controller is adjust the clock of interpolator to have 2 sample per symbol as an output. So the main core of the receiver is timing controller. It's the brain of the receiver. I'll explain its processing with complete details in a separate slide. But after interpolator, again, samples pass from a DDS for residual phase error compensation. The phase error is estimated by carrier recovery block, which is in fact a PLL for track the phase. After DDS, apply the match filter, and then the samples, the output samples of match filter are ready for use by the timing error detector. Estimated timing error is fed to the loop filter to be smoothed. Then the smooth value of error provided to the timing controller. Timing controller determine the error value and exact time of interpolation. In the following, in this branch, in the following, by downsample of by factor of 2, keep one of every 2 sample as output, which is used for phase. Also, this is as a final output, and also this final output used for carrier recovery and for phase error detection. Details also is available in the next slides. After transition time, I can show you a step by step. Here, RF signal drive DDS by the center frequency of signal. For example, center this signal, and after DDS keep the baseband harmony. Here, this signal filtered and other harmony removed, downsample, and by this factor, and calculate this downsample factor by this formula for have a number of sample per symbol after downsample about 4, not exactly. So the FS on line equal the FS over D factor divide on D factor. And after that, interpolator try to interpolate and compensate timing error and reach the sample per symbol exactly 2 sample per symbol. And here compensate again the residual frequency, match filter, and the sample are ready for timing error detector. And after that, timing error feed to the loop filter, and loop filter timing again provide the error value to the timing controller, and timing controller come on to the interpolator, and this loop close, and it's a feedback receiver, and also you can see the output appears something like that. After a transition time, the demodulator output will be something like that, which shows symbol synchronization and PLL work perfectly. So, or if the output of your receiver becomes something like this, it shows your receiver locked and work perfectly. But in the first slide of the main block interpolator, as I said before, the interpolator uses input samples. This is the input sample in the receiver. Use the input sample, somehow the timing error is corrected on it, as shown here. For example, the controller tricked the interpolator at this time. For example, at this time, the controller tricked the interpolator and commanded using the sample in time of MNTS and previous sample of it for and use them for interpolation. Interpolate a new sample which shifted mu NTS. Okay, this is the fraction part of timing error which is provided to interpolator for compensation. We can use cubic interpolation for this purpose. A formula of cubic Lagrange interpolator coefficient is here, and PUT as this summation is a interpolated sample, and XN is a input samples, and QN is a Lagrange coefficient as shown here. This formula is suitable for software implementation. So you can simply calculate the Q value by replacing the mu value and using input samples. Compute the sigma and yielding interpolated sample, name here PT. The more detail is available in this book by the Mayo. But for hardware implementation, you can use this structure for cubic interpolation. It's known as a FAR structure. For more details and familiar with other type of interpolation, refer to these Gardner articles. It's useful for hardware implementation. But here we just use this simple formula for interpolation because we here explain the software implementation, but it simply can apply for hardware. But about the Gardner timing error detector, the timing error detector proposed in the Gardner article is something like this. A structure of timing recovery in detail is something like this. I explained before, as I said earlier, Gardner timing detector needs 2 samples per symbol. For implementation of timing error detector, as you can see here, to estimate the error, the timing error detector is simply can be implemented by this formula. You can just by multiply the middle sample. It's a middle sample. This is a middle sample. This is a sample of current symbol, and these two belong to the current symbol. And you, by keeping just one sample from the previous symbol, you can simply implement this formula and multiply the middle sample. This is middle sample. Middle sample multiply at difference of current symbol and its equivalent sample from the previous symbol. So you can simply calculate the error. This is the middle sample. Subtract the sample of current symbol from previous sample of previous symbol, this part, and multiply it in the middle sample. Simply calculate this part. It's a real part, and this part belongs to the imaginary part of sample, and sum them each other and reach to the final error, timing error. So after calculate this value, pass it to the loop filter. You can use a second order loop filter, something like this. For smooth the error, as shown here, the second order loop filter, which is composite of 2 branch with KP and KI gain control, is used for adjusting the convergence speed. So put error here, and you can use this 2-line code, simple code, and calculate the output of loop filter. This first time calculate this, and after that is and this you use for another 6. It is very simple. But about the timing controller, I explained it earlier. Timing controller, as shown here, determine the base point index and the fraction interval. In the next slide, I'll show you how to implement it simply. Don't worry about it. But the work of timing controller again show here. Something like this is determine the base point index and the value of the fractional interval, and command to the interpolator to use this base point index and the fraction interval to interpolate a sample which is shifted mu k ts and exactly in this sample in this time. So implementation of timing controller, I explained it with a simple example. It's a very important part of receiver. Assume the FS underline frequency sampling after down sample in entrance of timing and PLL block is about 24.3 mega sample per second after down sample, and we have a signal with a symbol rate of about 4.5 mega symbol per second. So you know, as you know, your number of sample per symbol is possible calculate with this formula, FS divided by symbol rate. So the number of sample per symbol is about 5.4 samples per symbol. Here we use a fixed clock as I show here. Use fixed clock by this define a fixed clock by this formula. FS underline over 2 multiplied and symbol rate, and it's equal here in this example 2.7. In fact, it is a resampling clock for. In fact, it is a resampling clock, as you can see here. Resampling again occur here. For have a 2 sample per symbol after interpolation. For have a 2 sample per symbol after interpolation, it's a resampling clock. So we define it by this formula for have a 2 sample per symbol after interpolation. So it's defined by this formula simply. That means it's here for in this example here that's equal to 2.7 sample. That means for having 2 sample per symbol, with assuming 0 timing error. In the first step, we assuming we have a 0 timing error. For have a 2 sample per symbol, you should downsample the input signal by this factor, by this 2.7 factor. As you know, this downsample factor has a fractional part, so it is a challenging task. But with the help of interpolator, it is possible. With the help of interpolator and timing controller, you can simply overcome this challenge and downsample by factor of 2.7 for have a 2 sample after interpolator. Okay. So it is possible after passing 2 sample and before 3. It is possible treat the interpolator with the, for example, mu value fraction part. Mu I named the fractional part as a mu. Mu value equal to 0.7 by the mu value equal to 0.7. You can simply treat the interpolator for interpolation and compensate this error, this fraction part. and interpolate a sample for you. So it is you can simply implement and downsample with this fraction part and overcoming this challenge. So we define fixed lag equal to 0.7 as I calculated before, and we define a T controller. T controller is a timing controller. In fact, we define a T controller variable for counting the input samples. Here, for the first time, the first sample, its T controller equivalent is 1, and by coming the second sample, it's 2. T controller by third sample is updated to 3. This T controller equivalent of any sample. So, by entrance of sample 3, the T controller is greater than the fixed lag. So, we back to a sample ago. We back to a sample ago and define a T controller and use this T controller of the previous sample. I mean the value of T controller here is 2, and use this T controller value and calculate the mu according to this T controller value and calculate the mu. So the mu formula is every time the T controller greater than the fixed lag, we back to the T controller of previous sample and subtract the fixed lag from the T controller of previous sample, and we simply calculate the mu. Here is mu about the 0.7, and use a window of sample, this window of sample, for example this sample and 3 previous sample for cubic interpolation. If you use another type of interpolator, you can change the size of this window and derive this mu value as a fraction part to the interpolator, and using this window of 4 sample as shown, interpolator compute we name here interp 0 sample interp 0 in that time in this time. But after interpolation, T controller value changed should be updated by the new condition. So T controller value after this moment updated by subtracting T controller by subtracting the T controller of first sample from the fixed lag. You can update the T controller after this moment. It's about by subtracting 3 from the 2.7, it's about 0.3. So T controller for T controller updated to this value as the initial value, and for counting new sample after this moment, you update by the new initial T controller value. So the T controller of this value changed to 1.3 because the initial of after this moment initial of T controller is 0.3, and by coming the first sample after this moment, it's corrected to the 1.3 because first value sum with the residual from this moment, residual is 0.3, and by the coming the first, so sum this value residual part of T controller by the plus by 1. T controller of new sample is changed to the 1.3, and after the second sample, after this moment, T controller of second is from the sum of 1 by this by previous sample, T controller of previous sample, so it's changed to the 2.3, and third one to 3.3. So again, here T 3.3 is greater than the fixed clock. Again, we back to the previous sample, okay, and calculate the mu from this value, and mu is about the 0.4, and use this mu value and this window of sample for interpolation, and command the interpolator to interpolate another sample, name it's named it, number it to 1. This is the first interpolated sample, this is the second interpolated sample, and again after this moment, update T controller by subtracting this value by the fixed clock, and so after this moment the T controller value, residual T control value, changed to this value, and by coming the first sample after this moment, so we sum the 1 plus this residual T controller changed for this sample, changed to the 1.6, and by second it's add by 1, it's T controller of this value, this sample is 2.6, and for this sample 3.6. so again, this value is greater than 2.7, and we back to control a sample ago and calculate the mu, and by this formula, mu for interpolation is about the 0.1, and use the window of these samples, for interpolation by this mu value, and interpolate the number 2 sample. So we have a 3 sample here, and it's a time for calculate the timing error. Okay. It's a time for calculation of timing error. So this is the moment we can trick the timing error detector to calculate the timing error by, as you can see here, these two samples belong to the current symbol, and this is from the previous symbol. So this is the middle sample, and this is a sample of current symbol, and this belongs to the previous symbol. By subtracting the value of this sample from this sample and multiply in the middle sample, you can simply calculate the timing error here, and as I said, you can use the Gardner formula for this reason. Here, so estimate the timing error and give it to the loop filter, and the output of loop filter again used for correct for update the T controller. So here the new T controller is equal the current T controller, subtract from the this value of error. So here you update T controller, and also you can calculate. You should calculate the timing error here, but because the interpolated sample of before of this sample didn't exist, so and middle sample is 0, so the timing error here, if calculated, is equal to 0. So the timing error calculation clock is after every 2 interpolated sample. So it says, and because each symbol has a 2 sample per symbol, so the clock of timing error detector is in fact a symbol clock. So Uh, so uh, mm, timing error detector works with the symbol clock. As you can see, so you can simply count the interpolated sample and after every two sample interpolated, trick the Gardner timing error detector to calculate the timing error, and after update the loop filter value, and after pass the output of loop filter to the timing controller. Timing controller just need to update the controller and T controller equal T controller of previous minus the Gardner the output of loop filter or output of loop filter, and close the loop. So here I just I said you calculate the timing error, so you have to update the T controller and subtract that timing error from the T controller, and so initial T controller updated by the timing error. By this formula, subtract the timing error because it's in here it's present and it take a value because this this interpolated sample has a valid value, but here also you have applied the same formula, but here you can subtract also after the calculation of timing error by the Gardner, subtract from T controller as you can and update the controller of initial after this moment and also after this moment. But here is not needed because, as I said, timing error calculated by the symbol clock, and after every two sample interpolated. Simply, you can implement the timing controller. It's a very important part of receiver. But about carrier recovery. Carrier recovery, as I in slide 2, I explain about it. Here, after interpolated, we have a two sample per symbol, and the phase error should compensate. We should compensate the phase error and use the output of compensate the phase error, residual phase error here, and after that pass the sample from the match filter, and here after down sample by 2, here is the final output, and we carry recovery for estimation of phase error. Use this sample, use in fact the final sample, and here is the carrier recovery in details, structure in details. And so you can see here phase error. The first step is estimation of phase error. Phase error. For estimation of phase error, you use the final sample, in fact, and phase detector phase detector used for detect the symbol phase error compared to the reference symbol. Then error provided to a loop filter again. It's a loop filter of PLL, it's not loop filter of timing. The loop filter of timing is separate and separate than this loop filter. And after estimation of phase error, you provide it for loop second order loop filter of PLL, and after that feed it to a phase integration. It's a phase, in fact, is a phase accumulator, and this is a simple formula. Just update by the new value and keep in the register for another 6. This is what here for QPSK and offset QPSK modulation, we can simply implement the phase detector by the Costas loop formula. It's a Costas loop structure for calculate the phase error. As you can see here, sine an imaginary part, multiply that q, and minus and subtract from the sine q, multiply I. Simply, you can implement the phase error for offset QPSK and QPSK. And after the pass the phase error to the loop filter, and after that feed to the integration, the final phi should be compensated here on the interpolated sample. Here I present for you the streamized version of code. It's implemented in Matlab for demodulate the whole signal. So it is a streamized version. Here is a definition of match filter. How to because match filter is applied on the interpolated sample, and in fact, apply when we have 2 samples per symbol. So we define the space equal 2, and here is a low pass filter design. And after that, this is the main body. Main loop, in fact, main loop performed until the whole file demodulated, stream by stream. We read the stream, and here you can see by this syntax, and here apply the DDS, and after that we apply the low pass filter. Here we downsample the baseband signal, and the output of downsample normalized by energy. You can implement here AGC, but it's software just sufficient to you normalize by the energy of signal. And so, and after that we feed this signal normalized by energy, and feed it to the timing-PLL function, and stream by stream the output is saved in the symbol, and the symbol is a constellation, constellation of each stream, and it's work until the whole file demodulated. By here you can see the result, final result. The final constellation for QPSK, you can see something is like this, and for offset QPSK also is something like this. But you can you should considering in a transmitter for building offset QPSK, Q branch delayed half a symbol time compared to the I branch, as you can see here, a transmitter offset QPSK. So for implementation of the timing-PLL for offset QPSK, you should compensate the half a symbol delay to yielding a perfect, to reaching a perfect constellation. After translate the symbol to the bitstream, I display the bitstream using image tool, and by the frame length I calculate for our signal, and I estimated the frame length of the bitstream. It's about the 16,030 and 16,320 bits, and as you can see, if I order this bitstream with this value in each row, you can see here the sync word. I show you how to use the main program and how to demodulate your own signal. Here, as you can see here, my signal, my example signal here, practical signal, I recorded in a offset QPSK stereo 20 mega sample in a file by this name. It's a offset QPSK signal, and it's recorded by the frequency sampling of about 20 mega sample per second. And I put the address of my file here, and here I just need to put it's recorded as a INQ, so is a stereo, so I put an OC number of channel about equal to 2, and here modulation type, the signal modulation type is offset QPSK. I estimated before earlier, and it's a frequency, I mean, it's a carrier frequency of the signal, and it's a symbol rate. I estimated the symbol of my signal earlier, and also I estimated its bandwidth. I put from breakpoint here to show you what kind of signal I want to demodulate it here. Here this recorded file and the input file, I want to decide to, as you can see here, the center of this signal is about the 5.0, 5.5 mega. So I decide to demodulate this signal with this bandwidth. You can measure it from subtracting a start and a stop value of the frequency. But I just want to show you, I decide to demodulate this signal, and I estimated its symbol rate earlier and its center frequency of this signal earlier, and I put just in the program. I remove the breakpoint, and here I try to demodulate the whole of signal around the algorithm. You can see here it's the frame number of demodulation change in step by step. In every cycle, the algorithm demodulate and reach to the symbol. It's a symbol belonging to each stream, and use the symbol to bit conversion here and write the bit stream, and here is the address of my signal. So here this is a recorded bit stream. As you can see here, it's take a value because it's continuously is in demodulating. You can see here this value change continuously because the demodulation work continuously and try to stream by stream.